All right, guys, back here for set two for your response questions from the AP Physics C 2024 Mechanics exam. And I've already, again, taken a look at these questions. I've got them mostly solved out. This one should be a little bit quicker than set one anyway. So yeah, you can see the picture though. Now you have a block 2M that's on a hill that has friction, goes down, collides with block B, and then they both compress the spring, right? Very similar to set one, but in this case, you're asked to derive an expression for the speed of the block at time t1, and then derive an expression for the spring constant. Note that t1 occurs after the block goes down the ramp, but before the collision. So we can actually use conservation of energy to help us find that speed of the block at the very bottom of the ramp then. Note that the speed of the block is, note that the mass of the block, is actually 2m. So what I can say is I can say that the gravitational potential energy minus the work done by friction has to equal the final kinetic energy at time t1, that is, right? Let's write k1 actually for that then. So I do get that mg 2m rather times g times the initial height minus the work done by friction, which is going to be the friction force multiplied by the displacement d, is going to equal 1/2 times 2m multiplied by v squared then. Now I have to actually find the height. I can do that using trigonometry. Hi over d is equal to sine theta. So therefore, hi is going to equal d times sine of theta then. In addition, I can find the friction force because I can say that the friction force is equal to the coefficient of friction times the normal force. And in this particular scenario, the normal force is actually going to be 2mg cos theta, just that one component of weight that is pointing into the ramp then. So if I plug all of that stuff in, I can cancel out all of the 2m's, and I'm just going to do that to make things a little bit nicer, even though this question sucks in terms of expressions. You get GD sine theta minus mu times GD cos theta is all equal to 1/2 v squared then. So I can say that v is going to equal square root of 2gd all times sine of theta minus mu cos theta. Yeah. All right, that's not terrible. I mean, it's still kind of nasty. You still have to do a lot of substitutions, but just wait till this next part. Derive an expression for the spring constant. Well, now, once the block has actually gone down the ramp, it's not going to experience any new forces until it actually collides at the time t3 then, where it sticks to the other block. So you have that the initial total momentum has to equal the final total momentum. Well, for initial momentum, you have the block 2m, so 2mv from above has to equal the total mass times the final velocity. So we have to do that to figure out how fast both blocks are going to be moving after the collision. And then after that, we can use conservation of energy to help us figure out the spring constant then. All right, so if I plug in what I got from part A for V, and then I find VF, what I'm going to find is I'm going to find that VF is actually going to equal, let's see, this is fun, 2/3 square root of 2gd times sine theta minus mu cos theta. At this point, this is just kind of tedious, rewriting the same expression a few times. After that, again, while those two blocks compress the spring, you're going to have conservation of energy. So you have 1/2 3m times vf squared is going to equal 1/2 k times xc squared. So therefore, k is going to actually equal 3m vf squared over xc squared then. So that's fun. Yeah, if you plug in what you got for VF from conservation of momentum, that's going to simplify down to 8 mg sine theta minus mu cos theta all over 3xc squared. And that just looks lovely, doesn't it? There you go. There's your final answer. All right. Now we get to sketch our nice fun graph, but this time it's not for kinetic energy, it's for momentum of the block. So this one's actually quite a bit easier than thinking about kinetic energy because momentum is just related to velocity, and velocity is related to forces. So it's actually really easy to sketch this. You got a straight line going up, you got a constant line, constant momentum. Momentum of block A will go down a little bit because block B will gain some momentum. And then after that, you're going to actually have it go down to 0 while that spring compresses then. So if we use the principles of forces to justify from 0 to T1, block A experiences a constant net force. So P is going to be proportional to time then. All right. From T1 to T2, right, there's no net force. So momentum conserved. All right. At time T2, the collision happens. At T2, transfer some momentum to B at the collision. When compressing the spring, well, what do you have when you're compressing the spring? You have that the force is actually going to be proportional to sine of t, because this is kind of like simple harmonic motion. So momentum is going to be proportional to a cosine of t then. And what you're going to get is you're actually going to get that the momentum is going to start off by changing really slowly and then change really quickly, because notice again that the force of the spring, the force that the spring actually pushes back on the blocks with, that's going to get stronger as time goes on because the spring is going to be compressed more then. So that all matches our predictions then. Excellent. All right, let's go ahead and move on to the next page. We're almost done with the first problem, and this last part's actually really simple because it asks how the period is going to change if you actually end up changing the ramp where there's no friction. And the answer is actually just that the period is going to be the same. You might be wondering how I know that. Well, this is a mass on a spring, right? T is equal to root m over k, right, times 2 pi. And mass and spring constant are not changing. That's all the justification you need for this. There you go. Both periods have to be the same. All right, moving on to the next problem. Instead of a cylinder, you have a sphere, right? And you have linear drag instead. You're still asked to derive but not solve a differential equation that could be used to determine the speed. Start with Newton's second law, as usual for a mechanics differential equation. A is equal to dv dt, right? And then you have mg minus bv should equal m dv dt. There's your differential equation. Nothing else to do here. You're not asked to solve it. Good. All right. Sorry for that terrible ellipse. My tablet is kind of lagging a little bit. All right. Anyway. Okay, let's go ahead and move on. Now what you have is you have F drag versus time, force of drag as a function of time. And the question is to label when that drag force has to actually equal the weight. That is going to be when that drag force actually levels off, and we'll call that T subscript of T for terminal speed. Explicitly reference appropriate features of the sketch. The drag force became constant, and therefore velocity is now constant. because they're proportional to each other. This means terminal velocity was, this means terminal speed was reached. There we go. All right, suppose a student now throws the same sphere downwards with an initial speed, and you're trying to figure out the magnitude of the new drag force at terminal speed after being thrown downwards. It has to be equal to, because drag force should be equal to mg, which doesn't depend on initial velocity. All right, moving on to the graph, you have to draw a best fit line and then use your best fit line to calculate B. Hopefully you'll take my word for it that I drew a best fit line because I did on my paper. Yeah, I think that should hopefully be a pretty free point for all of us. If you do it, you get the point as long as you do it okay. So let's actually talk about how to use it. So you have that F drag is equal to BV, right? So that relates our two axes then. If I divide both sides by V, you get that the rise, which is change in F over change in V, is equal to your slope, right? So rise over run. And then therefore your slope actually has to equal B. The 2 points that I used were 20 comma 15 and 5 comma 5 on my line that I have on paper here. So that's 10 over 15, which means that B is going to equal 0.67, and the units this time are newtons times seconds over meters, because it's force over velocity then. All right, there you go, and there's our value for B then. Awesome. Let's move on to the next part. The next part is asking you about another experimental stuff, essentially saying that you're claiming that the terminal speed depends on diameter. Try to confirm that. What should you plot in order to do that? Well, let's just plot terminal speed versus diameter of the sphere. Right, justification is again pretty obvious for this one. I really don't know what they're expecting from you aside from just if there's some correlation between the two, then you put a power fit to it, and that'll give you the relation between them. I don't think I'm even going to bother to write that out right now. All right, let's move on to the third question then. So all right, you have a disc, you have a string and a clay, and there's an axle that's pointing out of the screen. This picture just looks really confusing. Essentially what's happening, and it took me a while and some help to try to figure out what was happening here because of that vertical pole. I thought that was the axis at first, but it's actually that axis pointing out of the page at the center of the disc. The disc is going to rotate counterclockwise, and essentially I think what that string is supposed to do is I think it's supposed to keep that lump of clay. I think it's supposed to keep that lump of clay attached to the disc at that point. So the clay is supposed to be stationary and the disc is supposed to be rotating clockwise in that direction kind of shown. So if we follow that interpretation, then I think this problem is going to be okay to solve, because now we have to draw the external forces on the clay disc system. Well, you've got gravity acting on both things. We don't actually know how the masses compare, so we can draw the gravities however we want. I'm going to call it FD for force of gravity on disk, FDG maybe, FCG for clay gravity. Then you've got tension pointing to the left on the clay. And you might be wondering, well, then doesn't the clay have a net external force? And the answer is no. It still experiences a normal force and or a friction between the clay and the disc, but those are not external forces, so we're not going to draw them. Likewise for the disc then, the disc is also going to end up experiencing a hinge force then, so we'll call that F hinge. This is just weird. You're drawing like two free body diagrams on the same picture, and I hate that. But those are all the external forces we should have then. As a hinge force, two gravitational forces, and tension. All right, derive an expression for the tension when the clay is at point A. This seems like it's going to be a torque question again, because we know. So I'm actually going to probably go back to the previous page to do this. So let me go ahead and erase my annotations. And let's go back to the previous page to figure out the tension then. Because I think I want that I want this diagram, the figure 1, to help me with that. All right, so you have two things causing torque then. Both the gravitational force of the disk and the hinge force are acting on the axle. So relative to the axle, only the tension and the gravitational force on the clay are causing a torque. And they're actually opposing each other. So net torque has to equal 0. Right, so that means that the torque caused by tension, which is going to be R F T sine theta, has to equal R mg cosine of theta then. And so therefore what you're going to get is Ft is going to equal mg cotangent of theta. There you go. So that's the first part of the next page then, is you just set the torques equal to each other on the clay and solve for tension, mg cotangent of theta then. So, all right, let's go over to part C then. So now you actually move the clay, and the question is, how does the new tension why is there still a string? What is this? Why is there still a string at point A then? What's it even holding? What? Is it I guess it's holding the disk in place then? This is so weird. Um okay. And sorry, for part B, it should be M subscript of D, not M subscript of C. I need to write that there. So that should be MD, not MC. All right. Okay. What's gonna happen to the tension? Well, the torque caused by tension is going to have to rise. I think tension's actually going to have to be stronger. Tension should be larger. So the reason why I would say that is because now the torque caused by the clay's gravity is actually going to be higher now. The reason why is because of its location. Right now, that gravitational force is exerted tangent to the disk instead of just like straight downwards, right, and not tangent. So that means that the torque caused by tension has to be higher then. But since r and theta are constants, what that's going to have to mean then is that the tension force has to be larger then. So it's all about thinking about how the net torque has to remain 0 still. All right, moving on to D, you now have a non-uniform disk and you're asked to actually calculate rotational inertia of it. This isn't too bad. It's just a little bit tedious because you have integral of r squared dm. This is an area mass density, not a volume mass density. Why they used rho, I don't know. Hey, that rhymes. It's the only way I can keep myself sane during these, I guess. And then since you have a disk, and a disk is like a circle, area for a disk is equal to pi r squared. So dA is going to equal 2 pi r dr then. So that's what we would plug in for dA. All right. So you get 2 pi times beta, which is 4, integral from 0 to the edge of the disk, which is 0.3. And then you have r to the 4th, actually, because you get that extra r from the mass density as well, dr. And then that's going to give you, let's see, 8 pi over 5 times 0.3 to the 5th power. That's just lovely. I've done this on my paper as well, thankfully. So that gives you an answer of 0.012 kilograms times meters squared then. There's your inertia. All right, you cut the string, calculate the magnitude of angular acceleration of the clay disk system. Yeah, cool. All right. So we know that net torque now is going to equal inertia times angular acceleration. So therefore, alpha is going to equal net torque, which is the torque caused by gravity from the clay divided by inertia. So that's going to equal R mcg over the total inertia, which is 0.012, plus, you cannot forget about the clay's inertia, 0.6 times 0.3 squared. It's a point mass. So, all right, I haven't actually worked this one out yet. So let's go ahead and crunch some numbers. On the top, you've got 0.3 times 10 for G times the clay's mass, which is 0.6. So you get 1.8 on the top. And then for the bottom, you get 0.054 plus 0.012. So 0.066. Okay, 1.8 divided by that is equal to 27. Oh my goodness, that's big. Makes me think I did something wrong. 27.3 radians per second squared then. All right, and there's your answer, and I do believe that we're done, but let me just go ahead and confirm that on the next page then. So if we move to the next page, yippee, we're done with our mechanics free response questions. All right, I know that E&M has an experimental design question on it. That's not really going to be fun. I hate doing those ones, but we'll get through it, I guess. I'll see you guys back here for the E&M questions then in the next video. Thank you for watching.